All right, CNT120, we're continuing on Chapter 4, and we just talked about routers. We're going to move into routing tables. Routers are going to maintain routing tables, and this is really a database of what networks are located where. So you could think of this as, in your brain, you have kind of like a little map in your brain of how I get to work, how do I get to the gas station to fill up my car, how do I get to my favorite restaurant, how do I get to this school or this place. You have all these in your brain. That's what the router does too. The router has in its brain, if you will, where networks are and how to get to them. And they rely on these when it receives a data packet, a chunk of data, it's going to look at its routing table and say, oh, to get to that network, I'm going to pass it out this port. To get to this network, I'm going to pass it out this port. And again, it's like a little mental map that you use of how you get places. The router does the same thing. And the routing table really is just a series of networks and the port and how to get there. That's all it really is. These are actually built by, I was going to jump ahead here, these are actually built by, I'm scooting down here, routing protocols. Routing tables are actually built by routing protocols, okay? I scooted ahead there just a little bit. Here's an example of a network, a series of routers. The router's going to have in its table where this network is. It's going to learn from this guy where these networks are. It's going to learn from router B where these networks are. And it's going to start building a table so that when this guy passes data, it looks at his table and goes, oh, you need to go here to get to that guy. So it's going to maintain a table of where those networks are and how to get to them. I pass it out this port or that port. Static and dynamic routing needs to be mentioned. Static routing is where a network administrator actually codes in, this is the route you use. That gets used sometimes. If you only have one route between two locations, there's no need to have the router consistently learn and update. You might code it in as, this is the way you go to get there. Kind of like when you move to a new area, you might only know one way to get to work. That's the way you drive every day because you're afraid you're going to get lost. That happened to me one of the first jobs I ever had. I moved to a new area, and that's the only way I knew to work. So I drove that way every day until I learned another way. That's a static route. Meanwhile, there's dynamic routing. Dynamic routing is where you tell the router, hey, go learn these networks, and you maintain whether they're up or down or whether they're broken or fixed kind of thing. And now it relies on the routing protocol to get updates, update its table, and keep an updated table. This would be like you listening to the radio for a traffic update or checking your phone for a traffic update to know, well, I don't want to go that way. That's congested. I'm going to go another way. The router's going to do the same thing. That's dynamic routing. It's going to run a routing protocol to maintain the routing table. Both are used, both have their place or their time that they get used. They mention all devices maintain a routing table, if you will. On a Linux or Unix system, if I use the route command, I can see it. If I'm a Windows system, I can use a route print. And if I'm on a Cisco router, I'm going to use the show IP route command. So on a Linux system, let me pull my VM up. If I type route, I can actually see the routing table my machine has learned. Well, it really hasn't learned much. Here's the link local, and then here is literally how I get out of this campus or out of this lab, if you will. It hasn't learned much, but there it is. There's the routing table for my Linux machine. If I pull, actually I should leave that open, that way I have that there for later. If I look at my Windows machine now, here's my command prompt for my Windows machine. If I do the route print, well, this is connected to a larger lab, so it's going to have a little bit more. Here's a few more things it has learned, but you also do see the loop back kind of thing, and then I do start seeing some specific nodes or entries out there, things that it has learned and how to get there. It's its route table. And again, this is stuff it learns and maintains so it has it for use. Okay, kind of like your little mental map in your brain. On a Cisco router, if I do a show IP route, this is what the router has learned, what is attached where. These networks are attached, or I should say these networks are directly connected off this port, network off this port. This network I get to via this port, via this IP, and I will get there one router away. This network, I go out this port to this IP, and I'm one router away. So the router is maintaining its own routing table. And again, it's going to consult that When a piece of data arrives at its doorstep, it's going to consult this routing table to know, where do I pass this packet? What port do I pass it out to get it to the destination? Now, the router uses different routing metrics to calculate best path or best route. While you do this too, kind of in your brain, if you had to, if there was a competition of, hey, there's $1 million in a duffel bag laying in the food court of blah mall, you're going to, in your brain, think real quick, how am I going to get there quickly? And then you might even look at the clock and go, well, at this time of day, I'm going to go this way because this other route's always congested. So in your brain, you're factoring a couple different metrics on how to get to that mall where that $1 million bag, duffel bag with $1 million in, so to speak, to get there and win the prize. Well, routers use a little bit more basic things, but they use things like hop count, how many routers away. Obviously, the more router, or I should say, theoretically, the more routers, the longer it's going to take. The bandwidth, delay or latency, load or, kind of the congestion on the link, MTU, the larger I have, the larger bandwidth link I have, the more data I can send per time, if you will. Cost, this is assigned actually by an administrator. I might have two links and one can handle more bandwidth and we want more things across, so we use the other ones as backup, so we put a higher cost on that. Reliability and topology kind of thing. These all get factored in, but it really depends on the routing protocol and which kinds of metrics get used. Okay? It really doesn't matter on the routing protocol which one is going to get used. So that brings us to routing protocols. Routing protocols are just that. They are protocols on my router that are designed to talk to and learn and build routing tables. They are actually there to build routing tables that are consulted when a data packet arrives and you need to figure out, where do I send this thing? And I use the example here, you listening to it, checking the traffic on the road, and using that to determine the best path I'm going to use to get to work, school, gas station, Nido, Burrito, or whatever happens to be. That's your routing protocols. A couple things we need to mention while we're talking routing protocols. They mention administrative distance, convergence, and overhead. Well, administrative distance, you're going to see this number. It's a number indicating the protocol's reliability, 0 to 255. That number ranges from 0 to 255. 0 being excellent, outstanding information, very accurate, very reliable. Meanwhile, 255 is horrible, bad, should not be trusted. We should not use that. Well, to give you a quick example, if I back up here, on this routing table we looked at, this number right here is that administrative distance. RIP assigns a number of 120 to the reliability of that information. It's kind of so-so information. Just giving you a quick example of that. Different routing protocols have different administrative distance assigned to them, so we know whether it's reliable, good information, or kind of so-so. Convergence time is how long it takes for a change in the network to be noted by all devices and all devices to have that information. While some routing protocols converge very slowly, meanwhile other ones do it very fast. So in other words, how quickly does everybody in an area know that a road is closed because there's a traffic accident? How long does it take for everybody to know that? Well, years ago with just radio, it took a while for everybody to hear that. Nowadays with phones, I can get information very quickly, sometimes almost instantaneously. That the modern network of, using Google Maps kind of thing and getting updates on traffic, that usually happens a heck of a lot quicker than the old way. Some routing protocols are going to converge quicker, some are going to converge slower. Overhead, some routing protocols are going to send a lot of traffic on the network to learn all the routes. Meanwhile, other ones are going to do it only periodically. So the ones that are going to send traffic all the time they're actually adding overhead to the network. They're actually adding traffic to the network to learn what's out there. Meanwhile, other routing protocols only do it occasionally when a change occurs. They have a lot less overhead. They add a lot less traffic to the network. The book gives us a summary. These are some common ones: RIP, OSPF, ISIS, EIGRP, and BGP. These are some very common ones you run into. In our first couple networking classes, we end up using these first couple to get you started. Later on in the upper level CNT classes, we have you use some of the other ones. That way you get some practice with them as well. Okay, so let's take a look now. Let's look at a couple details of these. One dimension administrative distance, they showed you a chart in the book of 0 to 120. I think I might have even filled one or two in for you. A directly connected network to a router is going to be 0. That is the best known path because it's the best information. I know it's connected to me. A static route, an admin configured in, is going to have an administrative distance of 1. And then as you see here, different routing protocols, as it learns things, are going to assign different administrative distances. And you notice RIP is 120 is kind of like the worst one here. It's kind of, 120 is about halfway between 0 and 255. It's very much mediocre information. Okay? And the idea behind this is if a router learns if it learns a path through RIP, and then it also learns a path to that same network through a different routing protocol, the one that's better is the one it's going to pay attention to. So it needs to know how good is this information. We have different categories of routing protocols. We have interior and exterior. Interior protocols are the ones used inside your network, inside your autonomous system, inside a company network. And they actually have two categories, distance vector and link state. Distance vector examples would be RIP, and link state would be OSPF and ISIS. Exterior are the ones used by usually your service provider, by the edge routers, exterior routers, and that would be something like a BGP. BGP routing protocol tends to get used by your ISP providers. And again, here we have our interior routers using things like RIP, OSPF, VIGRP. Meanwhile, your exterior routers are using things like BGP. So, let's now, actually I'm going to pause and I'll come back and talk about the routing protocols in more detail in the next podcast.